Welcome to Topcast, and to the third and second to last installment of my breakdown and discussion of Chapter 9 from the Fabric of Reality, Quantum Computers. Last episode on this particular chapter, I finished in a place where David wrote about his own contribution to the field, starting the field, many of us would say, by proving, in other words, mathematically demonstrating, how a new mode of computation could be harnessed. Today we're going further. Today, in terms of what I would say is some of the more philosophical, scientific underpinnings of how it is that quantum and classical are different to one another. And next episode, I will devote more to a specific practical application of quantum computing, Shor's algorithm. In that section, I'll go further into the mathematics than what the Fabric of Reality itself does in order to provide an overview of the algorithm. So we'll be doing a little bit of mathematics. Don't worry, nothing graduate level or anything like that, just enough to gain a little bit of deeper insight into what's going on and why. So this is why, as I constructed this series over time, it ended up being produced into discrete chunks itself. I realized that the section about Shor's algorithm really did require its own episode entirely, so that's why things are being broken up in this way. What I'm about to read today includes something I've read before in various other episodes, but not to do with this Chapter 9 episode, the It from Qubit stuff, and in some other episodes I've concentrated on a passage that comes up here because I just think it's so enlightening to tease out the differences between the classical and the quantum. As with much of David's content, it bears repeating. And anyway, not everyone listens to all of my episodes, so you may not have heard this before yourself. In this section, not only do we get a distinction between the classical and the quantum, but again, the discrete versus the continuous comes up, and how there has always been something quantum about the classical when it comes to computing anyway. Well, let's just read this section. And David writes, quote, "The classical theory of computation, which was the unchallenged foundation of computing for half a century, is now obsolete, except, like the rest of classical physics, as an approximation scheme. The theory of computation is now the quantum theory of computation. I said that Turing implicitly used classical mechanics in his construction, but with the benefit of hindsight, we can now see that even the classical theory of computation did not fully conform to classical physics and contained strong adjubrations of quantum theory. It is no coincidence that the word bit, meaning the smallest possible amount of information that a computer can manipulate, means essentially the same as quantum, a discrete chunk." End quote. So there we have it. The bit, the object from classical computation, is a discrete chunk, a discrete bit of information, literally. While the quanta is a discrete chunk as well, thought in some ways to actually be the defining feature of quantum theory. It shouldn't be, but in some ways, well, that's where the name quantum theory came from. But we do have a problem before us. In quantum theory, we've got this situation where many systems, all systems really, can only take on discrete values. Our go-to example here is something where, like an electron orbiting a nucleus, orbiting in scare quotes, corresponds to its energy. These energy levels are sometimes called orbitals. Again, while that term orbital might be misleading, the fact is that an electron can be in this or that orbital, this or that state, and not in between, apparently. The electron is stable in a particular orbital, perhaps located as close as it possibly can be to the nucleus. By as close as possible, I mean close as physically permitted, as close as the laws allow it to be. But it cannot be, even if we call that orbital the n equals 1 energy level, and we've got an n equals 2 energy level, it can be in either of those states, n equals 1 being the so-called ground state, where it has the least amount of energy, the closest it can possibly be to the nucleus, and n equals 2, the next energy level up, where it's a little further away, and then you have n equals 3, 4, 5, and so on. It goes on to infinity. It can be in any of these discrete energy levels, but it can't be in between, so we're told. There's no such thing as an n equals 1.5 energy level, even though there is physical space there that it could occupy. We never find it there. And we know all this because experiments can be done. One that I've talked about is the photoelectric effect. That's a subtly different kind of effect. But more commonly, if we are to understand things like spectroscopy, how when you put electricity, let's say, through a neon glass tube, you end up getting a particular characteristic color. And that characteristic color is made up of wavelengths of light, photons of light, that correspond to the difference between the energy levels of electrons orbiting the, for example, neon atom, neon nucleus, I should say. And calculations can be done. And those photons, when you do the results of when you measure, in other words, when you find the results of your experiment by doing such emission experiments, the emission of light from particular gases, those photons always have precisely the energy that you would calculate as the difference between the energy levels from where the photons are coming. In other words, the difference in potential energy between n equals 2 and n equals 1, say, you can calculate that energy. And then you do an experiment to test whether or not the photon that you're getting has exactly the same energy as what you would expect coming from that transition of the electron from the higher energy level to the lower energy level, and voila, it does. You have an explanation. It's all very neat. That's physics, isn't it? How wonderful. Okay, so that's one thing to keep in mind. What is sometimes said at this particular point when you're talking about these kind of experiments, where electrons are moving from n equals 2, the high energy level, to n equals 1, the lower energy level, is that the electron cannot possibly ever be halfway between n equals 1 and n equals 2. It is said it cannot occupy that space. And this is where the term quantum jump comes from. It used to mean, this term quantum jump, it used to mean tiny discrete jump, and was a great mystery, because how can you get from here at the n equals 2 position to there at the n equals 1 position without passing through the space in between? Nowadays, in business and other areas, quantum jump has come to mean a huge change. But that aside, do quantum jumps actually ever happen? Well, no, they don't. Erwin Schrödinger said as much, and David Deutsch also wrote about this. In fact, it's worth reading what he wrote about this in the Edge magazine in answer to a particular question. So let's go there. Here's the article. I won't read the entire thing, just the first few paragraphs, and you get the flavour of what's going on. The Edge magazine asked the question, what scientific idea is ready for retirement? And David Deutsch answered, quantum jumps. Quantum jumps are ready for retirement. Okay, so let's read it. In fact, he begins, this is obviously where I got it from. The term quantum jump entered everyday language as a metaphor for a large discontinuous change. It has also become widespread in the vast but sadly repetitive landscape of pseudoscience and mysticism. And he goes on to say, quote, the term comes from physics and is indeed used by physicists, though rarely published in papers. It evokes the fact that mutually distinguishable states in quantum physical systems are always discrete. Yet there is no such phenomenon in quantum physics as a quantum jump. Under the laws of quantum theory, change is always continuous in both space and time. Okay, maybe some physicists still subscribe to an exception that, namely the so-called collapse of the wave function, when an object is observed by a conscious observer. But that nonsense is not the nonsense I'm referring to here. I'm referring to misconceptions even about the sub-microscopic world, like when an electron in a higher energy state undergoes a transition to a lower energy level, emitting a photon, it quantum jumps from one discrete orbit to another without passing through intermediate states. Even worse, when an electron in a tunnel diode approaches the barrier that does not have enough energy to penetrate, so that under classical physics it would bounce off, the quantum phenomenon of tunneling allows it to appear mysteriously on the other side without ever having been in the region where it would have negative kinetic energy. The truth is that the electron in such situations does not have a single energy or position, but a range of energies and positions, and the allowed range itself can change with time. If the whole range of energies of a tunneling particle were below that required to surmount the barrier, it would indeed bounce off. And if an electron in an atom really were at a discrete energy level and nothing intervened to change that, then it would never make a transition to any other energy. End quote. I'll end the reading there. It's enough to say that the electron has this range of energies and range of positions. And that solves this issue. It's not that if you're in the n equals 2 orbital, you have a single energy, and if you're in the n equals 1 orbital, you have a single energy. You have a range of energies by virtue of the fact you are a quantum object, a multiversal object with this range of physical properties across the multiverse. Even if you're only ever observed to have one in a given universe when a measurement is taken. That has to be the case. And that's what the notion of discrete is. You will only ever measure one of them. But across the multiverse, all of the possible energies are represented somehow. My own modest contribution to this is an article I wrote, well, there we go, 10 years ago, 2014 I wrote this. And I titled it, perhaps I've overstated things here, but the title is An Explanation of How Most Physics Texts Get the Explanation of Photon Emission Deliberately Wrong. Okay, I say deliberately there, maybe that's a bit harsh, but they do get it wrong. We might say deliberately because they're deliberately avoiding the facts of reality and good epistemology. I'm not going to bore you by reading my own article. If you'd like to, you can look this up. It's called... you go to www.bretthall.org/light and you will find it. But I'm just skipping towards the end where I quote Schrödinger, among other people, as well as I provide links there to a number of YouTube videos, bits of text on the internet where physicists are actually using this notion of quantum jumps and getting things wrong. Like chemists don't quite make the same kind of errors, it seems to me. But that aside, what I write towards the end here, quoting myself, is, quote, but it's not only David Deutsch, because Schrödinger himself weighed in on this, writing, quote, I believe one is allowed to regard microscopic interaction as a continuous phenomenon without losing either the precious results of Planck and Einstein on the equilibrium of macroscopic energy between radiation and matter, or any other understanding of phenomena that the partial theory affords, end quote. And I go on to say, in other words, the results of Planck and Einstein, that electrons really are particles, parcels, is not affected at all by taking on the idea that transitions between energy levels happen continuously, just like a skydiver who falls continuously from the plane to the ground, end quote. And that harks back to something I say earlier, comparing this to the classical notion of gravity. Anyway, the central point here is that the electron has a range of energies and positions, and they can change over time. I'd further say that just because one never observes an electron at the intermediate position doesn't mean it can never possibly be there after all. That's the empiricist mistake. You can't see it, therefore it can't possibly happen. That's not true. At least modern day attempts to picture the electron around a nucleus have improved somewhat. You look up modern, cartoonish representations of what's going on with electrons around nuclei, and they represent it as this cloudy, wavy, probability distribution type thing. That gets closer to the truth than other representations that you can quite easily readily find in any book or on the internet anywhere when you look at how electrons are positioned around nuclei. Okay, some pictures are closer to the truth than others. The transition between n equals 2 and n equals 1, for example, can be continuous, even if those states themselves are discrete. And the photon so detected when you have photo emission from n equals 2 to an n equals 1 transition is always exactly the same energy or wavelength, frequency, color, whatever we want to say about that. Okay, David has more to say about this in The Fabric of Reality, so let's go back there. And David writes in The Fabric of Reality, quote, discrete variables, variables that cannot take a continuous range of values, are alien to classical physics. For example, if a variable has only two possible values, say 0 and 1, how does it ever get from 0 to 1? I asked this question in Chapter 2. In classical physics, it would have to jump discontinuously, which is incompatible with how forces and motions work in classical mechanics. In quantum physics, no discontinuous change is necessary, even though all measurable quantities are discrete. It works as follows. Let us start by imagining some parallel universes stacked like a pack of cards, with the pack as a whole representing the multiverse. Such a model in which the universes are arranged in a sequence greatly understates the complexity of the multiverse, but it suffices to illustrate my point here. Now, let us alter the model to take account of the fact that the multiverse is not a discrete set of universes, but a continuum, and that not all the universes are different. And that bears repeating. Let us alter the model to take account of the fact that the multiverse is not a discrete set of universes. It's not parallel universes like cards in a deck, but it's a continuum where also some of the universes are identical to one another. He goes on to say, in fact, for each universe that is present, there is also a continuum of identical universes present, comprising a certain tiny but non-zero proportion of the multiverse. In our model, this proportion may be represented by the thickness of a card, where each card now represents all the universes of a given type. However, unlike the thickness of a card, the proportion of each type of universe changes with time under quantum mechanical laws of motion. Consequently, the proportion of universes having a given property also changes, and it changes continuously. In the case of a discrete variable changing from 0 to 1, suppose that the variable has the value 0 in all universes before the change begins, and that after the change it has the value 1 in all universes. During the change, the proportion of universes in which the value is 0 falls smoothly from 100% to 0, and the proportion in which the value is 1 rises correspondingly from 0 to 100%. Figure 9.4 shows a multiverse view of such a change. And there we have a picture, a diagram of this continuous change between two discrete states, the 0 and the 1. The proportion of the universes change over time. That's the continuous aspect of this. David goes on to say, quote, "It might seem from that figure there that although the transition from 0 to 1 is objectively continuous from the multiverse perspective, it remains subjectively discontinuous from the point of view of any individual universe, as represented, say, by a horizontal line halfway up, figure 9.4. However, that is merely a limitation of the diagram and not a real feature of what is happening. Although the diagram makes it seem that there is, at each instant, a particular universe that has just changed from 0 to 1 because it has just crossed the boundary, that's not really so. It cannot be, because such a universe is strictly identical with every other universe in which the bit has value 1 at that time. So if the inhabitants of one of them were experiencing a discontinuous change, then so would the inhabitants of all the others. Therefore, none of them can have such an experience. Note also, as I explain in chapter 11, that the idea of anything moving across a diagram such as figure 9.4, in which time is already represented, is simply a mistake. At each instant, the bit has a value 1 in a certain proportion of universes and 0 in another. All those universes at all those times are already shown in figure 9.4. They're not moving anywhere, end quote. And this leads to this idea of time being in the instant that I've said before. This comes from Julian Barber. Time is in the instant. And so here's a particular case where we notice that you can only possibly observe 0 and 1. These are the only states that exist, and this explains how you get from the 0 to 1 in a continuous way, because the proportion of universes are changing over time continuously. And again, I say over time, but even that, that is sort of, that takes time out of the multiverse in a sense, which isn't true. And it says there that no one experiences a discontinuous change. You don't have that experience. What you experience is measuring something. You measure a 0 or a 1. The two states that exist. You'll never catch it halfway in between. It's in one place or the other, even though it moves from one place to the other continuously. But the laws only allow you to measure these, whatever the object is, in the state 0 or 1, in either 0 or 1, one of those states. You don't measure electrons at the intermediate point. You experience 0 or 1, or n equals 2 and n equals 1 orbitals, okay, energy levels there, or any of the other discrete values that are permitted. But to get from n equals 2 to n equals 1 or whatever quantum state to whatever other quantum state, the transition that happens is continuous across the multiverse, as I've emphasized and David said. But you don't see that. There is movement through space even if you do not experience it. Again, the demand that you should, or that somehow that would be a refutation of all of these facts, is just an appeal to empiricism. But as we always say here, there is just so much in science, perhaps most of the interesting stuff, we just never do see and cannot see, even in principle. David goes on to say, quote, "Another way in which quantum physics is implicit in classical computation is that all practical implementations of Turing-type computers rely on such things as solid matter or magnetized materials, which could not exist in the absence of quantum mechanical effects. For example, any solid body consists of an array of atoms which are themselves composed of electrically charged particles, electrons and protons in the nuclei. But because of classical chaos, no array of charged particles could be stable under classical laws of motion. The positively and negatively charged particles would simply move out of position and crash into each other, and the structure would disintegrate. It is only the strong quantum interference between the various paths taken by charged particles in parallel universes that prevents such catastrophes and makes solid matter possible." End quote. So just remember, this harks back to something that was said earlier in the Fabric of Reality about this distinction between classical chaos type theories and the quantum. In the quantum, you occupy a particular space. You occupy a particular place. You can't have infinitely small changes, which you can have in classical physics. And these infinitely small changes that you could have if the world, the universe, physical reality was governed by true classical laws of physics would mean that you have these amplification effects that lead to chaos. The disintegration of atoms, in other words. It's only the quantum, the interference, that allows these things to be stable. David goes on to say, quote, "Building a universal quantum computer is well beyond present technology. As I have said, detecting an interference phenomenon always involves setting up an appropriate interaction between all the variables that have been different in the universes that contribute to the interference. The more interacting particles are involved, therefore, the harder it tends to be to engineer the interaction that would display the interference. That is, the result of the computation. Among the many technical difficulties of working at the level of a single atom or single electron, one of the most important is that of preventing the environment from being affected by the different interfering sub-computations. For if a group of atoms is undergoing an interference phenomenon and they differentially affect other atoms in the environment, then the interference can no longer be detected by measurements of the original group alone. And the group is no longer performing any useful quantum computation. This is called decoherence. I must add that this problem is often presented the wrong way round. We are told that quantum interference is a very delicate process and must be shielded from all outside influences. This is wrong. Outside influences could cause minor imperfections, but it is the effect of the quantum computation on the outside world that causes decoherence. Thus, the race is on to engineer sub-microscopic systems in which information-carrying variables interact among themselves but affect their environment as little as possible. Another novel simplification, unique to the quantum theory of computation, partly offsets the difficulties caused by decoherence. It turns out that unlike classical computation, where one needs to engineer specific classical logic elements such as and, or, and not, the precise form of the interactions hardly matters in the quantum sense. Virtually any atomic scale system of interacting bits, so long as it does not decohere, could be made to perform useful quantum computations. Interference phenomena involving vast numbers of particles such as superconductivity and superfluidity are known, but it seems that none of them can be used to perform any interesting computations. At the time of writing, only single-bit quantum computations can be easily performed in the laboratory. Experimentalists are confident, however, that 2 and higher bit quantum gates, the quantum equivalent of the classical logical elements, will be constructed within the next few years. These are the basic components of quantum computers, end quote. So even now, this is still true. So let's change next few years to next few decades. But you cannot predict the growth of knowledge. David knows this better than anyone else, and whether or not these people are confident or not. Some are very confident. Some are so confident they think they've already done it. You read some of the marketing material from these people. So I'll talk about that in a moment. Let's just we'll complete this part of the text, and then we'll discuss some of the hazards about trying to figure out what's going on with the state of quantum computation at the moment. David goes on to say, these are the basic components of quantum computers. Some physicists, notably Rolf Landauer of IBM Research, are pessimistic about the prospects for further advances after that. They believe that decoherence will never be reduced to the point where more than a few consecutive quantum computational steps can be performed. End quote. It's just worth saying, look, again, if it's physically possible, then all it requires is knowledge. Someone saying that they don't believe or they don't think or they're not confident that something such and such can't happen, but they don't have a physical law they can point to, who cares? I think we just have to wait and see. It's taking longer than what some people might have expected, but again, our expectations are themselves a form of intuitive feeling. So again, irrelevant to physics and epistemology, largely. I've interrupted myself again, so let's keep going. David says, quote, most researchers in the field are much more optimistic, though perhaps that is because only optimistic researchers choose to work on quantum computation. Some special purpose quantum computers have already been built, and my own opinion is that more complex ones will appear in a matter of years rather than decades. As for the universal quantum computer, I expect that its construction too is only a matter of time, though I should not like to predict whether that time will be decades or centuries. The fact that the repertoire of the universal quantum computer contains environments whose rendering is classically intractable implies that new classes of purely mathematical computations must have become tractable too. For the laws of physics are, as Galileo said, expressed in mathematical language, and rendering an environment is tantamount to evaluating certain mathematical functions. And indeed, many mathematical tasks have now been discovered which could be efficiently performed by quantum computation, where all known classical methods are intractable. The most spectacular of these is the task of factorizing large numbers, end quote, because that will lead us into next episode where we will talk about how to factorize these large numbers using Shor's algorithm, but that's for next episode. I just want to finish with a few remarks about the state of the experimental work on this, because it's something I've taken some interest in, because I think I've mentioned this before many, many times on Topcast. I just happen to live near a particular university, my alma mater, the place I used to go to study. I didn't study quantum computation. It wasn't a thing at that university at that time. I knew about quantum computation only because I read The Fabric of Reality, but otherwise it sort of didn't exist as a field at the university I was at. But now, not only does it exist as a field, you can do whole degree programs in it, and it's a very active area of research. Anyway, David's given us a hint there of what some experimentalists are doing. As I say, it's a very interesting area of research. But it's one of those places in science where commercial in confidence knowledge, intellectual property, copyright stuff, and so forth, which the investment into this stuff can only be paid for, or rather the research can only be paid for by hefty investment to pay the people to do the expensive experiments. And those investors typically want a return on their investment. And so at times we've got perverse incentives operating. Namely, some companies don't want to share the advances they're making because they want to invent the thing first and then be able to have a copyright on it so that they can market it and sell it and have an advantage over the competitors. And that seems to kind of slow things down in this area. Or does it? Because it might also speed things up if you've got actual competition going on in developing these things via various competing approaches, various competing architectures, different research communities, different universities, different nations are trialing different quantum systems as quantum computers. At the moment, they're all having, it seems to me, about the same level of progress. But who knows? The tension between competitive commerce in the free market and the open sharing of information that happens in science, I don't know where to lay my bets on that. What would be faster? If somehow it's kind of like you want the mixed economy here, but I don't advise that either. I don't know what the answer is. Should everyone just share all of the information, in which case there's not an incentive for wealthy people to invest in this area? Or should everyone keep all of their information very commercially and confident, so you get the big investors by hinting at them that you've got the idea, you've got the special road to progress, road to the universal quantum computer? I don't know. As I say, my old alma mater at the University of New South Wales, which has this centre for quantum computation, it's a place where our own federal government invests heavily, but also you have private industry investing, a whole consortium of universities are working together there on this thing, funding this thing. So these people have hundreds of millions, maybe billions of dollars. Even the US military is involved out there at the University of New South Wales with funding this stuff and helping them with what they're doing, because it's a defense issue as well, because after all, if you have the first universal quantum computer, then you break RSA technology. That's an issue for the financial markets. That's a national security issue, and so on and so forth. Now, the University of New South Wales is interesting. It seems to me, as an outsider, again, I don't know anything except that I went there and I checked the website now and again, but beyond that, I don't have any deep insight into it. They do seem to publicise their results everywhere, in journals and on their website. And the interesting thing here is that although their progress and progress elsewhere on quantum computation appears to be quite slow, other areas of their research moves on apace. So what I'm saying is their work in quantum computing also bears on related important problems in physics. High temperature superconductors, improved laser engineering, manipulating individual atoms for nanotechnology purposes and all that sort of stuff. So the growth of knowledge is unpredictable. So even if there is a sense in which you might be failing at your goal, so to speak, your goal of building a universal quantum computer, the goal might not actually be the point, but rather the quest is the point. It's not the destination, but it's the journey and all that. Along the way, you discover new avenues, new technologies and new techniques and so on that can potentially change the world, even if the way in which you wanted to change the world with the universal quantum computer remains a little elusive for now and for the next few decades or centuries even. But, it's exciting to track these things. And epistemologically, it's interesting for me as well, because you do get those private companies from time to time who announce they've got a fully functioning quantum computer of some kind or other. But you rarely get the details. In other words, it's all very much kind of Theranos in quantum computing, if you know what I'm talking about here. That company that claimed they could do blood tests with just a finger prick of blood, and they got billions of dollars worth of investment and made some temporary billionaires. You get this sense sometimes in the field of quantum computation with some of these companies out there saying, "We've got it. It's what in modern parlance is called a grift. It's not all a grift, though. We know these things are physically possible. I guess we know that a pinprick of blood is, in principle, physically possible in terms of able to reveal just about every disease that you've got. Okay, but we're not there yet. What David Deutsch did was to prove these things, quantum computers, universal quantum computers, are physically possible. We're waiting now on the engineers and experimentalists to catch up to his vision. And he's the first to admit that, he's absolutely amazed by the work they do. Experiments are hard. Engineering is hard. But what we can thank David Deutsch for is knowing that these other scientists and engineers are on to something, even if it's demonstrating many of the ways these devices won't work. Iterate and repeat, guess and check. That's how all progress is made. Until next time, bye-bye.